Hey guys, this is my lab for Lab 3. So to introduce it, we were given a star with a known trajectory and mass, and this lab challenged us to determine the mass of an unseen object, which was a black hole, based on the given information. So we were observing the star's motion in order to detect the net force on the star. And then similar to the second lab, we are going to use GlowScript to update a computational model that supports Newton's second law and the momentum principle, as well as Newton's universal law of gravitation. Then some key concepts that connect what we were doing in this lab to what we were learning in class would be that we are studying the parallel and perpendicular components of momentum, as well as how F net relates to the derivative of momentum with respect to time, as well as studying more with gravitational forces. So the second law states that the acceleration of an object is dependent upon two variables, the net force acting upon the object and the mass of the object. And then Newton's law of universal gravitation states that every particle attracts every other particle in the universe with a force which is directly proportional to the product of their masses and inversely proportional to the square of the distance between their centers. So for this lab, we had to make some assumptions. And the first thing was that we had to create this unique trajectory for our star and then assume that the time between the given data points in the code and our specific trajectory was 1 day. Second, we had to assume that the black hole was located at the origin and then that the only net force on the star was gravity due to the black hole. So in this lab, we needed to program equations that applied the momentum principle and Newton's law of universal gravitation. We used equations derived from the momentum principle in order to compute the initial and final momentum vectors, in order to calculate the star's change in velocity and change in momentum, as well as to calculate dp over dt, and then the parallel and perpendicular components of those as well. We then programmed equations based on Newton's law of universal gravitation to calculate F net and the parallel and perpendicular components of F net. And then lastly, we applied Newton's second law to update the current position and velocity to show the object's current track. We were able to do this by using a while loop and increment the time stops after each iteration, as well as advance the index to step through all of the data points. We had to include the initial conditions of our object's mass, initial position, and initial velocity that we got from our data. So after adjusting the code, I calculated that the magnitude of the net force was 9.99 times 10 to the 28th newtons. Then I calculated that the parallel component of the magnitude of the net force was 2.6 times 10 to the 28th. And then the magnitude of the perpendicular component for the net force was 9.6 times 10 to the 28th newtons. And then I used equations to calculate the mass, and I got that was 1.76 times 10 to the 34th kilograms. So we are to discuss how the net force and its parallel and perpendicular components are different from the rate of change of momentum and its parallel and perpendicular components. So first, the direction of the perpendicular forces for F net and change in momentum will always point in the same direction, and their magnitudes will always be the same. So I think that the biggest difference would be that if the force were to get bigger, there would be a sharper turn and the radius of our circle would actually be smaller. But on the other hand, if momentum were to get bigger, the time would stay the same, but there would be a smaller change in direction, and so the radius would actually be getting bigger. However, for the parallel components, if momentum were larger, the parallel component of the force's change in direction would be smaller, and thus the radius of the circle would be larger. And then lastly, is it possible for us to find a value for the mass of a new black hole that is different from the mass you found in the original one? Well, I don't think so, no, because you wouldn't be able to tell a difference because all the values would be constant. R would stay the same, the constant G would stay the same, and the gravitational forces would not change.